Hello, everyone. Today we're going to delve into a pressing concern surrounding the rapid advancement of machine learning and artificial intelligence, their security. Recent studies include one by the National Institute of Standards and Technology, or NIST, sheds light on potential threats and attacks facing these models, urging us to explore mitigation strategies. Before we delve into the security aspects, I think it's important to acknowledge the remarkable growth of AI. From research laboratories to real-world applications, AI has become ubiquitous, deployed across diverse domains such as healthcare, finance, and transportation. However, this further highlights the need for proper security measures. The interesting challenge that arises with AI attacks is that these attacks aren't confined to the digital realm. Physical attacks, like manipulating stop signs to deceive autonomous vehicles, pose real threats. Additionally, the sheer volume of data used to train these models presents a monumental challenge. For instance, the corpus used to train GPT-3 was a staggering 568 gigabytes of raw compressed text, equivalent to about 400 billion tokens. Properly cleaning and maintaining this data is nearly impossible, amplifying the risk of injecting false information into training sources. Most security risks found in software today are found in bugs and unsafe programming techniques and methods. However, AI is still so novel that it's difficult to identify these possible risks. NIST, in response to an executive order to ensure trustworthy AI, is diligently working on addressing these concerns. In their paper, they highlight the four main attack types that they foresee will arise in the future: evasion attacks, poisoning attacks, privacy attacks, and abuse attacks. Unfortunately, these attacks happen at different times in the deployment pipeline, only further exacerbating the need for proper security at every step. Evasion attacks. Evasion attacks occur post-deployment, aiming to alter model responses by manipulating inputs. For instance, injecting misleading prompts can deceive large language models, resulting in detrimental outcomes such as insider trading tips or, as seen here, ingredients for napalm. Another type of evasion attack is tricking image recognition software by placing tape on a stop sign or on the road to trick self-driving cars to perceive it as something else and either swerving into the other lane or not stopping. Poisoning attacks target the training phase, enabling attackers to manipulate data. Examples include inserting inappropriate language into chatbot corpora so the chatbot incorporates that information into its responses, or subtly varying image labels. These compromises compromise model integrity and pose significant challenges to learning accurate representations. Examples shown here are adding some noise to the image of a panda causes the model to completely change its prediction to a gibbon, which highlights the sensitivity of these models and the importance of securing the training dataset. The other example shows generative images based on increasingly poisoned examples, which, as we can see, leads to more nonsensical results. Privacy attacks occur during deployment, seeking to extract information about the model's training or decision process. Attackers may exploit vulnerabilities by probing dataset origins, compromising sensitive information. This only highlights the need for robust privacy-preserving mechanisms. This example shows a study that was looking into finding the demographic information from a speech recognition model. Just by using the model, they were able to get an idea of the demographics of the training data that was used for training. Abuse attacks. Abuse attacks involve injecting false information into training sources, impacting model reliability. For example, corrupting widely used sources like Wikipedia can lead to models absorbing false information, undermining their effectiveness, and emphasizing the challenge of monitoring and cleaning vast training data. NIST recommends techniques such as adversarial machine learning, where models are trained with altered inputs to recognize and mitigate potential attacks. By incorporating these attacks into training models can enhance stability and withstand adversarial challenges more effectively. They also recommend incorporating cryptography techniques in securing the training data to prevent attackers from altering them, and using keys to detect alterations if there are any. In conclusion, securing machine learning models and AI systems against cyber threats demands proactive measures and constant oversight. As these technologies pervade various domains, ensuring their security is paramount for building trust and reliability. NIST's efforts, alongside ongoing research and collaboration, are pivotal in achieving trustworthy AI systems. Let's prioritize safety and leverage available knowledge to navigate this evolving landscape.